Hello explorers and welcome to another video. Today we are going to talk about QR codes. And QR codes are actually something that we use not that often anymore, but it can be really helpful if you want to set up a place where you print out something and somebody scan that and you get a URL, for instance, or if you want to have product information by scanning a URL and so on. So they have a very large benefit, and because of how they are built with a lot of error correction and so on, they are very hardened, so they will work even though the picture might be not that great. So this is a very interesting technology, and there are so many things that I can say about it and talk about. But I'm gonna go through how a QR code works, and I'm gonna start with how to draw a QR code and how to read it if you want to know how it's built up. And then I'm gonna go into more of a coding exercise and show you different parts of it. One part that I will leave out because I don't really understand it and I will not figure it out at the moment, I have no interest in doing so, is the actual error correction part. If we switch over to my screen here, we can see a document that describes this. So the error correction is done using polynomial long division. So you have a lot of polynomials and then you do a long division over them in some specific method. And it seems like a lot of different programmers have struggled with this as well. So what I found was one C implementation that was done by a mathematics student, and then everyone else has just copied that solution over and over again. So there isn't that many actual implementation of this error correction. It's the Reed-Solomon error correction. So it was done by two professors, Reed and Solomon. And the good thing with this error correction is that if you're missing a part of the message and you have a correct error correction, you can actually reintroduce the missing parts by just looking at the error correction and doing some math. So that's really interesting, but I'm not going into that because I don't really understand it. So let's look at my code here. And I'm gonna start with actually looking into how to draw a QR code. So I created a QR code drawer here, and there is a lot of different parts in a QR code. So let's see here. First off, we have so here we have my QR code drawer. We put in a version number. Let's start with a small one, version 1. And a version number is how large the QR code is. And the version number starts at 21 modules by 21 modules. And this is a standard QR code. There are a lot of deviations and different other standards for similar things that you could put in the same family, but this is the original QR code. And then I also added a module size of 5 pixels, and modules are the actual drawn element that you see here. So if we run this code here, we will get an empty QR code with the amount of space needed to draw these modules. And the specification says that you need to have 4 modules outside here, outside the actual drawing area with white, in order to not confuse the algorithm to find the actual QR code. So you need some white space outside. Let's see. Let's start with the finder pattern then. So the finder patterns, these are these boxes out here. So those are very commonly shown in the QR code. And the important part to see here is that you have a center of 3 by 3 modules, large, and then you have a white square around that with one module, and then a black square around that with one module, and then you need to have white around that again. So this is the important part to find where the QR code is, and you see these finder patterns in all standard QR codes. So if you see something that looks like a QR code and these three fields are missing, then they are not a standard QR code, then it's something else. Then we need these alignment patterns, so let's draw those and see if we get any at all. We didn't get any alignment patterns because those are probably not shown in this smaller version. And then we have the timing patterns, and these are lines that go between the QR code like this. Perhaps we should switch up to the larger version so we can actually see the alignment patterns as well. So here we see the alignment patterns, and you see those are similar to the finder patterns, but they are smaller. So they have one module in the middle, three around that with white, and then black around that. And if we remove the finder patterns, we can see that these alignment patterns are underneath those as well, but you don't draw them if they have a finder pattern over them. And these timing patterns, these lines, these are dotted lines on the sixth column and the sixth row of the QR code in order to see how large is a module. So you can use these in order to figure out how large is a module and how should I read this QR code. And then another important part is to have a dark module, and this is one dot that they put in order to have other parts of the document make sense, because this would be a data module if it wasn't specified as a dark module, because it's not evenly distributed. So they needed this dark module, and it's always present. And I'm not sure if you can see it. It was in by the lower QR code finder pattern, you have one dark module. So that's another important part. Then we need to know what kind of version is this, and if we have a version that is beyond 7, so it's a larger than 7, then we have a version. And you see here from the lightest red to the darkest red how these binary bits are presented. So they display the version number in columns and rows like this, drawn out on the QR code. And if we go down to, let's say, version 5 here, then the QR code is so small that the version number is not added because you can figure out how large it is anyway, and the version information is not that important anymore. Next up, we have the masker information, and this information tells you what kind of masking has been done on this QR code. We have both a format and a mask in this QR code, and the mask is a way to change different modules from black to white in a specific pattern. So you have the QR code, you draw it, and then you run a mask over it using an algorithm, switching out some of the modules. And then you do that 8 times on this, and you get different QR codes. And then you validate those 8 QR codes and see which of these are the best to display to the customer, so to be the most readable. So we have something that we will change up the QR code in a specific manner to make it more readable, and that's called a mask. And the format string, that's an interesting and important part as well, because you have 4 different formats. You have L, which is low error correction, and it can restore 7% of the data. You have M, which is medium, I guess, and then you have 15% of the data that you can restore. You have M, which is medium, I guess. Q, which is quality, perhaps, and that's 25% of the data. And then you have high, which is 35% of the data. So this format and masking string will indicate what format is it presented in, and also what masking have you done on it. And the last part is adding the data. So I run this little function here, and it will add all the data to it. And you see here that the data flows, it's a little bit hard to see, but it actually goes like a worm, up and down, up and down, up and down, skipping line or column 6. So it jumps over column 6. And it goes from the rightest most and then to the left one, and then it goes up in a zigzag pattern. And then when it reaches the top, it switches over and goes down again in a zigzag from right to left again. So it's a little bit strange way to put in data, but it makes for good readability. So that's why they have added it like this. So now I have presented how a QR code is drawn, what parts are available in a QR code, and how to draw those. And this is a very interesting thing to implement. It took me, I think, 2 nights to implement the drawer. And I think that's a fascinating project to do in itself. And there is a lot of different things in the QR code that you can just implement because it's fun to think about a problem and try to implement code that can do that. So let's look at a real QR code then. Let's create this QR code here. And this QR code is a numeric QR code. It's level 1. It's using level L, so it's quality level L. It's using version 1 and has mask 0 and a size of 216 elements. And drawn like this. And it's a working QR code. And you can put your data in as either numeric, alphanumeric, byte, or kanji. But you can also mix all of these because they have a header element, and then you have the length and then the data. And you can put as many of these as you like in order to compress your data as much as possible. I wanted to look into actually an algorithm to figure out when should I use numeric, when should I use alphanumeric, and when should I use byte, for instance. But I haven't come to that yet. I might implement that later. It's an interesting thought exercise, but it's not that important. I've implemented numeric, alphanumeric, and byte so far. I don't use any kanji. I don't understand kanji, so perhaps that's something that I will skip in my implementation here. So first off, we need to encode some data. So let's look into the encoder here. And in my case, I've chosen, let's see if I can make some room here. So I've chosen to implement this in a lot of different iterations. So this is the end result, where I've added everything into a character encoder and so on. But if you want to write some data, I have a string builder where I will put all the bits, and these are bits of information, so 0 or 1, and I put that into a string because that's an easy way to handle bit streams. And I will append the length and also what encoding to do. And if we go into this function, it will look at the current encoder and get the bit ID. And I've added those up here. So the bit ID for numeric is 0001, alphanumeric 0010, and byte is 0100. So you put the bit 1 over for each of these. And then I need to know how many of these numeric is in the specific version. And usually there is 10, and if you reach a specific point, it's 12, and then 14, and I have the breakpoints here as well. So 0 up to 9 is 10, 10 to 26 is 12, and 27 and up is 14. So that's why I use these breakpoints. An encoding string is which values are allowed in this specific encoding. So here we have 0 to 9, and then alphanumeric has a lot of other characters, and then in byte we have all the characters. I just put that to null. So when I encode a message, I go in here, I check if I want to do numeric, alphanumeric, or byte. And the numeric string is a string with 3 numeric characters, up to 3. So there I put a pattern here that takes 1 to 3 numeric characters. And if I find a length of 3, then I will parse that as a specific value. So I will go from start to end and then parse that into an integer. And if the length is 3, I will write that as 10 bits of information. If we only have 2, then I will write that as 7 bits of information. And if we only have 1, then it's 4 bits of information. So that's how I handle the numeric string and how it's specified to be done. If we want to encode an alphanumeric string, we have a matcher here that matches on this pattern that we had up there, and then between 1 and 2 of them, so I will have either 1 or 2 of these alphanumeric. I will pick out the length, and if the length is 2, I will take out both values and look at the position in this string where the char is, and get that value, and get the index of that value in my encoding string. And that index for the first character will be times 45. So the specification says just time it by 45. And the second one is just added to that. And you will give a length of 11 bits to save that information. And if you only have 1, then you will save that as a 6-bit string. So these are a little bit more involved ways of writing information, because if you want to write a byte, you just write the value of that byte as an 8-bit encoded value. So I started this by just implementing the byte sequence because that was very easy. I just want to write a byte every time. So now we have a way to write data, and that's the first thing I do up here. And after I've written the data here, it goes through and sees how many bits have I written and how many bits is available for this version in this quality. And by doing that, I can figure out how small can I make my QR code and still have all the data in it. So I will make the QR code larger depending on how much information I put in. Because of the breakpoints that we talked about earlier, that some of the information is written in a larger format, or you have a larger length information in larger formats, I needed to figure out if I went past a breakpoint, then I had to write the information again. So that's what I'm doing here. I write it again, I get a new version. So if we have my QR code here and I write something like a long lorem ipsum, this will create a very large QR code, and it requires a lot more information, so that typically over the breakpoint, because it's version 25 using mask 2. So that's why I write it again after I figured out how large it is, because I need to change the information about about the length of information. After that, we need to add some extra bits, and those extra bits are just added if there are either a few bits left in this version. So I get the bits allowed in this version, and if that's smaller amount than 4 extra bits, then I will only add that. Otherwise I will add 4 zeros to terminate my string. So that's something that you need to do. And then you need to add extra zeros so you get an byte equivalent amount of data. And so I just do a modulus of 8, so I will get 8 bits. And if I have some extra bits that needs to be added in order to get it to an even amount of bytes, then I will add some extra zeros there. And after that, the specification says that if you haven't filled out the whole information in this QR code, you need to add some extra data just to fill it out. And you should add 236 and 17 as bytes to the encoding stream until you have filled out all the data bits. So that's what I do here in this while loop. Next up, we have another fascinating thing that you need to do. I have a thing that separates these bytes into groups, and the groups are a specific length depending on your version and your quality. So these are groups of either 1 or 2. So if we go in here, we see that we have blocks in group 1, and then we have the words in that group. And the blocks is, let's say that we have 2 blocks of 16 keywords in group 1, and then we can have 2 blocks of 15 in group 2. Then I need to separate these both into the different groups, but I also need to have the amount of them in that group. So what I do here is that I go through the number of blocks in the group, and then I will create ranges of that amount in there. So let's say that we have this example that I told you about. 2 blocks of 16, then I will have 16 words, and then 16 words, and words are just bytes. So 16 bytes, 16 bytes, and then 15 bytes, 15 bytes. So that's why they have separated into 2 blocks, because they can't really get an even amount of bytes otherwise. So sometimes you just have number of blocks in group 1, could be 4 blocks of 16 words, for instance. And that's everything. You don't have anything in group 2. But if they don't get an even amount, they will use that. And if we look into my version file here, you see that I have both encoding for the version, but then I have a lot of information here about how many bits are in each group. And that's from a table. I will give the link to the tutorial in the description here, but these are the values of groups. So you have, for instance, here group 1 is just one block in this, and there we have the number of words in that block. And then we have 0, 0 in group 2, for instance. But this changes depending on the version. And here we have the amount of error correction blocks per block. So if we, for instance, have 2 blocks of 16 words and we have error corrections of 7, then we will have one of the 16 have 7 error correction blocks, and the next 16 will have 7 error correction blocks. And depending on if we have multiple groups of them, it can be very interesting to implement. So we split it up into groups. And then I just take the number of error correction blocks for this quality and this version. And then I go through each of these splitted groups and do generate these error correction blocks. We will not look into that implementation because I don't understand it. It's just something that takes a number of bytes, returns a number of bytes. And this longest group here is when we have 2 groups. I wanted to know how many words we have in the longest group, so I can use that in order to interleave them. Because of course you need to interleave the groups if you have multiple of them. So that's what we're doing next. So here we have something that goes for the amount of longest groups and then through each of the length of the groups. And here we will take the first word from the first block of group, and then the first word from the second block of group, and then the first of the third block of group, and so on. And then we take the second word, and so on. So we will take them interleaved. So we will not get first every block in the first group and then every block in the or every word in the second group, or so on. We need to do first group, first word, second group, first word, and then when we have switched over and taken all the groups, we will take second word in first group, second word in second group, and so on. And of course we need to do the same with the error correction words. So they are also interleaved depending on how many groups you have. So yeah, the same principle. The only thing is that you have one error correction block per data block. And last but not least, you need to add a few bits because a QR code could either end up to be exactly the amount of data that you have using the error correction and the data, or you can have 3 or 7 bits that is larger than. So there is a definition on how many extra bits you need to add to each version in order to make them fully filled, but it's never above 7. So I add 8 zeros because my algorithm will not draw further than when it has drawn every data block available in the grid. So adding 8 means that I will always fill out the extra parts, even if it's some extra bits that are added. So that's the way to create the data stream. And it is a lot. And then I have some functionality to actually switch over and get all the bytes of a specific bit string. I have tried to use BigInt and a lot of other things in order to separate these, but it doesn't really work well. So this was the way for me to actually get the correct byte out of a string of bits. So that's another thing you can look into and figure out how to implement. Also a fascinating task. Let's see if we have anything else to talk about here. No, not really. So that's the data encoder. How to encode your data. And I have some tests for the data encoder here to see that it does the right things. Could also be interesting to look into. I have the link to the full project in the description of this video. And let's see. The character encoder we went through and talked about. So now we only have the masking part left. How to do the actual masking. Drawing the QR code is an interesting task. You can look into the draw functions, but just to don't make this video multiple hours, I'll not go into that. But the masking could be interesting to talk about. And the different algorithms to draw a mask is either you take the column and the row and then modulus that with 2, so that's mask 0. Then you can take just the row, modulus 2, and with 0, column, modulus 3. And these are the places where you need to switch out black and white modules. So where you have a dark module, you will put a light module, and when you have a light module, you put a dark module, if they coexist with these rules that you have here. So you will create 8 masks, and when you have done that, you need to calculate how good is this mask. So I first create all the masks here, put them into an end result. I finalize them. Finalize in my case is that I draw them with color first, and then the finalize goes through and puts in the dark and light material. And that's just because I don't want anything to draw over something else. And by using the colors, I could say, here you have the green place where all the data should be, and then just draw the data into the green squares. And where it's not green, there is something else that you should not touch. So that's why I have this finalize function here. And then we will create something that figures out the smallest penalty, and we will calculate a penalty here. And we can see in our output here that we have different penalties for each of these, and the smallest value is the number 2 mask. So that's why it's chosen. And how do you calculate the penalty then? Well, you do it with 4 different rules. And these are also interesting. Rule 1 is just calculating through calculating through each row and each column. If you have some place where you have 5 or more of the same color, you will give it some extra penalty. So let's say that you have 5 dark modules, then it will get a penalty of 3. And if you then have an extra over those 5, let's say that you have let's say 7 dark modules in a row, then you will add 3 plus 2, so it's 5 in penalty for this calculation rule. So in every module over 5 will get an extra penalty added to it, and the first 5 will get 3. So that's the first calculation rule that you need to do. Calculation rule number 2 looks at colors in the grid and adjacent to those. So this will look for 2 by 2 squares and see if those have the same color. And if so, it will give it a penalty of 3 extra. So squares of 2 by 2 in anywhere in the grid will give you a little bit extra of a penalty. Then we have rule number 3. And the third rule is actually looking at the specific pattern. And if we look at this pattern here, we have bit 1, 0, 1, 1, 1, 0, 1. And you can see this pattern again in the actual finder pattern of this QR code. So we are looking for finder patterns and then close to that empty spaces. So if we find anywhere where we have the finder pattern plus 4 empty spaces on either left or the right side or above or below them, so we'll go in both directions in order to see that. And if you find that in anywhere in the image, you will add a penalty of 40 to that. So it's a very strict or large penalty for finding that specific pattern, because that's a very bad thing for readability. So you need to have as few of those as possible. And the last one is very simple. You count up the light parts and the dark parts, so you get all the light modules and all the dark modules. And then you will take the minimum of that and divide that with the maximum times 100. So you will get a percentage of the light and dark modules. And then you will take that and do an absolute on the percentage divided by 5. And you do a ceiling and a floor of that. So you will get an upper bound and a lower bound. And then you will take both of those and remove 50% from those, and an absolute value of that again, and then we'll divide that by 5. And when we have gotten that difference, we will take the smallest value of those and time that by 10. So this is how I understood this specific calculation rule. But in the guide here, we have all of these calculation rules printed out. So let's see here, data masking. So perhaps I have understood it incorrectly, but everything is presented here. So this is the algorithm that I followed. So dark modules, divide that and get a percentage, and then you do a minus and you get a difference there, and then you take the smallest value of those and divide by 0, and then multiply by 10. And in this case they multiplied 0 by 10 and got no result. So everything is in this guide, but I thought that was really interesting to implement these different rules and get those to work correctly in order to get the smallest penalty and the best masks available for this. And when you have done the masking, you are pretty much done. You just need to print everything out and create your image, and you should get a QR code that is readable. I know that there's a lot of moving parts in a QR code and it can be hard to follow. I hope that you at least understood how the QR code is drawn in a more structural way. You don't need to know everything about the QR code if you're not implemented it. But I thought that this is pretty much as fun as doing the code challenges from the advent of code, because each of these steps are small, verifiable things that you can implement in order to build a larger picture. And I got a lot of gratification about when I created my first QR code and it was readable. I could take a reader and read my QR code. That was amazing to do. And it really was a fun project to take on, even though it might be a lot of things to get to work. If you have some extra time and you want to have a fun coding challenge, I think this is a very interesting one. If you ever are interested in implementing your own, please leave a link as a comment to this video and I will look at it. It's a very fascinating topic. Perhaps you will implement a way to actually encode the bits in a very efficient manner. That would also be very interesting to hear about. I hope that you found this video interesting. I know that it was a bit long. I hope that you liked this video. If you have any comments or suggestions, leave them down in the comment section down below. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.